Okay, picking up where we left off, we're going to continue on with the graphs. All right, this time the information says that we've been given a unit on the y scale of half a mile. So they've changed it from feet to miles, but a half mile. So we're looking at 1. Let me mark this better. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so 8 miles are marked along the vertical axis. I know I'm having trouble because I'm not using my pen. All right, so back to question 1. We're going to calculate the distances covered over those 2 time intervals. So we know that we have 1, 2, 3 and a quarter, roughly. So over the interval from 0 to 2. The object has traveled 3.2 miles, 3.25 miles. You might call it 3. I don't know. Depends on how close you think that is. Let's call it 3. All right. And over the time interval from 4 to 6, so from 4 to 6, it looks like it's just 1 mile. All right. If we want to calculate the average velocities, well, we need to take the change in distance over the change in time. So for the interval from 0 to 2, we're looking at 3 miles in 2 hours. Right, or 1.5 miles per hour. And on the interval from 4 to 6, we're looking at 1 mile in 2 hours, so a half mile per hour. So now if we want to estimate the instantaneous velocities at the 2 specified times, that's at time t equals 1 p.m. and t equals 4 p.m. Right, we could use an average velocity. We would like to find the slope specifically at time t equals 1, but in order to do that, we could use the time interval surrounding. So we could do s of 2 minus s of 0 divided by that change in time, which is 2 hours. Okay, if we call s of 2 I'm just checking. If we call s of 2 3 miles and s of 0 0 miles, okay, we still get 1.5 miles per hour. At 4 p.m., using 3 and 5 as our surrounding interval, we'll use s of 5 minus s of 3 Again, it's over a 2-hour time interval. And it looks like S of 5 is 4.5. No. S of 5 is 5. And S of 3, 1, 2, 3, I don't know, 3.75. Again, as long as you show your work, your estimate's going to count, even if it's not exactly going to match what mine is. So we're going to have 1.25 miles over 2 hours, which is 0.625 miles per hour. Okay, so the only way to find an instantaneous rate of change from a table or a graph is to use an average rate of change as our estimate. Okay, new graph, S of t, will still measure distance. S of t is equal to t squared, so it's a nice parabolic graph. All right, t is on the horizontal axis. How can we find the object's instantaneous velocity at a particular point in time, for example at t equals 2? So here's t equals 2, it's the point 24. And again, here we are on a graph. We can use the slope of a tangent line to estimate the instantaneous velocity. So if we attempt to draw a tangent line, and estimate its slope. Right, so someone might say that slope is 3, someone might say that slope is 2. An estimate might be 2 meters per hour if we're talking meters and hours. Okay, on the function s, the point 24 has been labeled along with an arbitrary point a squared. That makes sense because if you plug in a into the function, you're going to get a squared. So what does the quantity s of 2 represent? S of 2 equals 4 meters, and it represents the position of the object at time 2 seconds. Position of the object at time equals 2 seconds. All right, what does the quantity S of A represent? What is its value? Okay, well, S of A is going to be A squared. All right, and that's measured in meters. And again, it's the position of the object at time A seconds, if we're measuring time in seconds. Okay, total change. So we're just talking about the difference, S of A minus S of 2, which is A squared minus 2 squared, or A squared minus 4. All right, that's a change in position. If the object is at A squared and it used to be at 4, the difference, that vertical distance, right, is a squared minus 4. If I want the average velocity, we're going to take that total change, s of a minus s of 2, and divide by a minus 2, that change in time. So we could look at this as a squared minus 4 over a minus 2. Again, just recall that's the slope of the secant. Okay, so we want to move closer and closer to a formal definition of the instantaneous velocity. And to do that, we're going to take a look at these symmetric intervals. Okay, if we look at these intervals, we're looking at intervals on the right-hand side of 2 and intervals on the left-hand side of 2. And we want to find the average velocity over each of these intervals. So here we're looking at s of 2.1 minus s of 2 over 2.1 minus 2. All right, so 2.1 squared minus 4 over 0.1, and that simplifies to be 4 meters per second. Here we have s of 2.01 minus s of 2 over 2.01 minus 1. All right, so 2.01 squared minus 4 over 0.01 is 4.01 meters per second. All right, if we continue on with each of these calculations, 2.001 squared minus 2 squared over 0.001, we get 4.001 meters per second. Here, 2.0001 squared minus 4 over 0.0001 seconds, 4.0001 meters per second. So you can see in each of these calculations that our value, 4.1, 4.01, 4.001, we're getting closer and closer and closer to 4. All right, looking at the right-hand side, we're going to take a look at s of 2 minus s of 1.9 over 0.1. Or 4 minus 1.9 squared over 0.1. Here we have 3.9 meters per second. The next interval from 1.99 to 2, 2 squared minus 1.99 squared over 0.01 is 3.99 meters per second. Two squared minus 1.999 meters squared over 0.001 is 3.999 meters per second. And the last one is 3.9999 meters per second. So again, the intervals on the right, 3.9, 3.99, again getting closer and closer to 4. So we're going to estimate that the instantaneous rate of change at t equals 2 is 4 meters per second. All right, got to stop this video.